Hi, welcome to Weekly Physics and CSZC with Sir Ben. Today we're going to discuss dielectrics as a continuation of our discussion on capacitance, and of course with capacitors. If you're wondering where do we use capacitors, we use capacitors in our electronic devices such as computers, laptops, TVs, so that they have a stored charge. One example of a stored charge is in our emergency light. So if there will be no backup power, there will be no source of electricity, our capacitors can give off electric charges until it will be drained. If electric charges will be given off by our capacitors, then our materials or our electronic devices will function. Now, as I've mentioned a while ago, capacitors that we have illustrated are capacitors that contains only vacuum as our dielectric material. But what would happen to capacitors if we insert a non-conducting material or insulating material? What would happen to our capacitors? To further understand that particular question, we need to understand also the nature of dielectric materials. Dielectric materials are insulating materials that is inserted between two conducting plates. So the question is, why do we need to exert or why do we need to insert dielectric material between two conducting plates? There are three reasons why we need to insert dielectric material between two conducting plates. The first one, so that the conducting plates, the two conducting plates will not be in direct contact with each other. And of course, if we insert a dielectric material, the capacitance will increase because we will be reducing the electric field strength of the capacitance or of the capacitor between two conducting plates. As you have seen in our simulator a while ago, that there is really a strong electric field presence due to the attraction of the two conducting plates. But if we insert a dielectric material, the electric field will decrease. Later on, we will know why. And of course, if we insert a dielectric material, we will reduce the possibility of shorting the circuit or shorting the capacitor because the conducting plates will be in contact with each other. Okay? There would be a mix-up of electric charges and that would sort to short circuits. Now, the most common dielectric material are dielectric sheets. They are used to separate the two conductors. Now, the most common type of capacitor uses dielectric sheets and they are formed into a cylinder one. They are parallel plates, parallel sheets, but they are formed into a cylindrical one. Now, in this illustration, we have the conducting material in a with or the metal foil, and between the two conducting material is a dielectric material, or in this case, it's a plastic sheet. Plastics are are non-conducting material, so they have a poor ability to conduct electricity or to allow the flow of electric charges. We are using insulating material so that will the electric charges will not jump off from one conducting plate or from a higher potential to a lower potential because the insulating materials have a poor ability to allow the flow of electric charges. Now, as you can see here, if we if we have a vacuum as our dielectric material, meaning there is air, no dielectric our dielectric material is air, the potential difference is increasing. The potential difference is increasing. But if we place a dielectric material between the two conducting plates in our capacitor, the dielectric material will, or the electric potential will decrease. Why? Why is that? Because we are lessening, or we are reducing the electric field strength. Remember that the electric materials are non-conducting materials, so what will happen to them is that they will allow the process of induction, wherein there would be a polarization of electric charges. So the electric charges inside the dielectric material will become polarized, or will reposition themselves to pair with the other electric charges. As you can see here, this is the electric field of a conducting plate without the electric material. So the electric field is very strong. But if we insert a dielectric material between two conducting plates, what happens? There is an isolated pairing of electric charges. So there is an isolated attraction. This is because of the induction process. There is a polarization, an isolated polarization of electric charges. So there is a pair here, and a pair. So if there would be an induction process happening here, then there would be no electric field present. So if there is a positive, negative here, the other one is the negative side. So all the negative charges will, in the dielectric material, will go to the side where the positive charges are, and all the positive material or positive charges will go to the negative side where the negative charges are located of the conducting plate. So there is an isolated polarization. If we do that, the induced charges will allow the decrease of electric field strength. That's why if we compare the two diagrams, there are lesser electric field lines in illustration B. Now, what would happen to the capacitance if we reduce the electric field? The capacitance will increase, and the capacitance of a material is identified, or yes, identified using this equation. So this is a derivation, how we derive this particular equation. So the capacitance with the capacitance is directly proportional to the area of the capacitor, or of the conducting plate, which is separated with a distance r. This is from our previous equation, which is epsilon naught times A all over D. And since we have inserted a dielectric material to make it so that we can fully see that the capacitance is increasing, or would affect the dielectric material, would be a factor of the change in the capacitance of the capacitor, we will be writing down another constant, which is represented by a Greek letter kappa, which is a dielectric constant. Now there are two two notations that we can use. We can use a dielectric constant and a dielectric strength. Now, primarily for capacitors, we use dielectric constant. Now, every dielectric material has different dielectric constants and dielectric strengths. So we have C for capacitance with a unit of farads, potential difference of volts, Greek letter kappa for the electric constant, Q for charge, and so on and so forth. Now let's put this equation to the test. And in so doing, we can try this problem. If I have a parallel capacitor plate without a dielectric material, and it has a capacitance of 2 microfarads, which is connected to a battery of a potential difference of 12 volts, how much charge is stored in the capacitor? And if I'm going to insert an ebonite dielectric, what is the charge also stored? So I have here the working solution, two working solutions. And now let's try to compare which is greater than the other. Okay? If I'm going to, this is without the electric material. So the total amount of charge present is 2.4 times 10 to the negative 5 coulombs. But if we insert an ebonite capacitor, the electric material, it is increased to 6.0 times 10 to the negative 5 capacitor. So it only shows that the dielectric material increases the capacitance or increases the amount of electric charges stored in our conducting plates, having a constant capacitance. Now let's try another problem. We have a capacitance, so we are to find the capacitance and the potential difference that can be applied to a Teflon filled parallel plate capacitor, and it has an area of 1.75 centimeter square, and they are separated with a distance of 0.04 millimeters. So our dielectric material is Teflon. So how do we do that? So we have here, we need to determine the capacitance of our system, of our capacitor. So we have Teflon, the dielectric constant of Teflon, which is 2.1, and we converted 1.75 centimeter square to meter square, and of course our distance. Okay, now this is okay. So we have, if we go along with the process, we have here what. So let's try to see. I think I made another mistake here, so my apologies. So if we have epsilon naught, so I'm using now my calculator. Uh, we have epsilon naught. I'm using a Casio 991 PS Plus. So if I'm going to press Shift 7, that would allow me to choose the constant value, and epsilon naught is number 32. Okay, and I'm going to multiply it by 0.000175 times the Teflon, the electric constant, divided by 4 times 10 to the negative 5. Why? Why it's negative? Because it's from millimeter. Okay, it's from millimeter. Okay, so that will give us 0. So the capacitance is equal to 8.131, or 8 point in my calculator it's 8.134, because I used the whole number of the whole values of our permittivity of free space. But if we only use 8.85, that will give us 8.131 times 10 to the negative 11. So this is not 7, this is 11 farads. So we have here 8, no, 8 times 10 to the negative 11 farads. So that's the capacitance of our capacitor. A Teflon we're using Teflon. So right now, we need to identify also the maximum potential difference that can be applied in our capacitor. Of course, we cannot use a dielectric constant because the electric constant is only used for capacitance. So if we want to find the allowable potential difference of a material using our dielectric material, we can use the dielectric strength, which is dependent also in the number or in the material. So the dielectric strength of our Teflon is 60 times 10 to the 6 volts per meter. You can just look it up, and then we multiply it by 0.04 times 10 to the negative 3 meters. So this is the distance r. Okay, this is the distance r. Okay. This is our distance r. That will give us 2,400 volts. So this one, if you can see, this was 4 times 10 to the negative 5, but this one is 0.04 times 10 to the negative 3. So what I did is I just moved the decimal places. Okay, from here I moved the decimal place. I just moved the decimal place. Okay, so if we move 0.04, we will convert this into 4.0 times 10 to the negative 5. It will move 2 decimal places after the whole number. So if we do that one, that will give us a potential difference of 2,400 volts.